All right, why don't we get started? My name is Dean Wampler. I work for TypeSafe. You can actually get the slides right now off that polyglotprogramming.com link, like where I keep all my presentations. And some of the photos will be of the London Eye. I was in London a couple of weeks ago, so I'm inflicting my photos on you. Okay, so let's see if this is going to work. It won't work unless I plug this in. I've written a few books for what it's worth, but mostly the last few years I've been doing big data stuff, a lot of Hadoop, and then seeing all the pain points with Hadoop. And some really exciting things are happening in the data space that actually represent sort of a coalescing of a bunch of trends. So in a lot of ways, some of the things we're going to see today, you've already seen several times today if you went to Brian's keynote and to Roland's talk on reactive streams, because you're going to see the same sort of metaphors where we seem to be coalescing on how we should really process data in the most efficient and intuitive way once you understand the metaphors being used. And that's really why Spark is so interesting in the next top compute model, as I claim. So I'm all about this big data stuff and Scala, or maybe this is what I'm really all about. I'll let you decide. This is actually a real book. It's in the Harvard University Library. It's about fishing, the original form. Okay, well, first, how many of you have ever worked with Hadoop at all? All right, how many of you have actually written to the Java APIs? All right, I can see the pain in your faces. How many of you actually have used Spark? Anybody actually played with Spark before? Okay, a few of you. All right. So circa 2013, this is like just right up to the end of last year when the Hadoop community more or less kind of de facto embraced Spark. But just to catch the rest of you up to what Spark is, or rather Hadoop is all about. So this is what schematically a typical Hadoop cluster would look like. Hadoop being this, the big data, big elephant thing that everyone talks about as what you want to use if you have very massive data sets. And they've been re-architecting the system to be more robust and fault tolerant and so forth. And it more or less looks like this now, where you're going to have some replicated, federated master nodes that are responsible for two major pieces. Actually three, we could say three pieces, one of which would be resource management, like I can allocate so many processes on this node because I know how much CPU capability it has, how much memory. I can schedule jobs, that would be like the second part. And it used to be those two were kind of glommed together in a very discombobulated way. And then there's the third part, which is the file system, which we won't really talk about, but it's the underpinnings, how you store the data, how you organize it. And as well, just for the sake of completeness, you can also talk to databases like your NoSQLs and your SQLs. Sometimes you'll see that integration happen as well. But just in the simple case, we'll assume that we're going to put all our data in the Hadoop distributed file system. And we start off then managing jobs, managing resources with this master resource manager process that used to be called the job tracker, but now it's separated into some things I'm not even showing you as well. And on each node, there's going to be a node manager that understands how many resources that node has available and so forth. So when you actually submit a job in Hadoop, whether it was the old version of Hadoop or this current version 2, the resource manager or the old job tracker decides how to decompose your job into tasks. And it's usually like one task, which means the JVM process, per block of data in the file system, and blocks in the Hadoop file system are 64 meg or some multiple thereof. Very big, much bigger than you would typically see in a file system. And they do that so that you get contiguous data on disk and you're not losing time seeking across the hard drive. You just park the heads and start scanning data or writing data. So a lot of little background stuff to make it fast, even though the whole system is actually incredibly slow in some respects. But you lose, or rather you win by concurrency, right? If everything is slow by itself, but you're running a million of them, then hopefully you're fast in the end, is really the model that Hadoop has always been based on. And then for completeness, there is this name node, and these things are paired because it used to be with one of these, if the name node went down, you were kind of offline until you could recover. So to keep it up, you can federate name nodes, you can shard the data, the responsibility of the file system. And you get this vast distributed file system that can scale up to hundreds of terabytes, even I think they might be able to get to exabytes now, but nevertheless, you know, master nodes, data nodes are responsible for the actual blocks on each server and so forth. And that's all I'm going to say about HDFS. It's not really the theme of the talk. But the way that we have traditionally written the actual compute jobs that are going to work with this data as opposed to store it is with this so-called MapReduce model that Google actually pioneered over a decade ago, wrote a classic paper about it in 2003, and then about the same time a guy named Doug Cutting was working on Lucene and some other tools like that, and decided it was a perfect model for what he was trying to do. So that's sort of the, without filling in a lot of details, that's kind of how we ended up with Hadoop. If you're wondering where the name comes from, by the way, that was the name of the little yellow toy stuffed elephant that his son was playing with at the time. That was the name of the pet, so that's what he used. That's why the mascot is an elephant. Funny story about that little elephant. For a while, he was carrying it around for keynotes, you know, sort of the totem of the religion, if you will. And then apparently the family dog ate the thing, so that was sort of an ominous metaphor for the future of Hadoop, I guess. But the model is very simple. It is very flexible, but not in important ways. But it basically is this. You have a first step called a map step where you read in the data and you do some preliminary processing. Everything is key value pairs, as we'll see. Then you know, this is all happening in parallel in a bunch of processes over this cluster, and then those key value pairs are going to get, you know, sorted and shuffled around the cluster to a reduction step that will finish the job. And that works okay for relatively simple algorithms, but it's not unusual for you to have to do a sequence of these steps. And one of the big problems with that is that it writes everything back to disk at the end of the reduce step. So you get this huge inefficiency of its writing, doing a tremendous amount of I/O when it's just going to turn right around and read it back in with the next job. But just architecturally, it was never designed to be smart about those sequencing of steps. But nevertheless, you can actually do it. And just to show you an example so that you can now, you know, go to your cocktail parties tonight and explain MapReduce to your friends, I'll actually walk through a very classic algorithm. It's called inverted index, and it's really the basis of search engines. It's the situation where I'm going to crawl interwebs, and I'm going to find all the documents and all of the words in those documents, and then build an inverse index of word to document so that when I search for the word Hadoop, I'll know what documents I should return to the user right away, which is why we get very fast responses from Google or whoever. So there's some process that's going to be running, you know, constantly. These web crawlers, if you've ever looked at your web logs, you've seen just, you know, gazillion entries for these things showing up. They're going to find pages. I just made up 3 that I claimed are in Wikipedia for Hadoop HBase, which is a NoSQL database in the Hadoop space. And Hive is a SQL query tool that we'll actually come back to. One of those books I wrote is actually on Hive, and I'll have a backstory about that. But anyway, so I find all these pages, and I'm just going to write a very simple 2-element table. I'll actually write it into the Hadoop file system as like key value, tab delimited data, whatever format you want to use. But it's just going to be the URL or maybe some ID to, you know, compress the amount of space I'm using. Doesn't matter, but we'll just go with URL. And then the second column will be just whatever was in that document, the entire contents. Maybe I strip out the HTML, maybe I don't, you know, whatever you want to do. So that's sort of setting up the data for MapReduce. Now we start the MapReduce job, so every now and then, and this is very much a batch mode system. I want to read all the data into memory, do my crunching on it, and write it back. So maybe I do this once an hour or once a day, however often I want to update this index. What if I want to update it as soon as a web page has been changed and I hit it with the crawler? Well, we're kind of stuck, and that's where we need new tools, as we'll see. But anyway, these are big blocks of data, and I'm going to spawn one map task. Hadoop does this for me. For each of those blocks of data, it will actually locate that JVM process on the server that has that block. So that's going to read it in, and then the map task, all it has to do is take each line in that table that it read in, which will have the URL and the contents. It's going to tokenize the contents, and then it's going to write out this new key value pair, or actually a lot of them, And it'll have, the key will be the word, and I'm using tuple notation here. So, you know, you'll see the word Hadoop, the word provides. You know, I know that some of the text in the diagram is maybe a little small to read from the back, but you can get these slides off my web page if you want to read the details, including the speaker notes. But anyway, so I'm going to write out this tuple, that the key is the word, and the value will be another tuple, which will be the URL, and then the number of times I saw that word on the document. That's also interesting information, right? Because I'd certainly want to return the web pages, when you search for them, that are obsessive about Hadoop, and not the ones that just sort of mention it in passing. So the count is actually kind of interesting, too. And this process continues out of each map task. And then there's this magic sort shuffle process that Hadoop does automatically, where it sorts locally within each mapper, you know, by key. And then it's going to shuffle all of those key value pairs to the reducer tasks, so that I end up with all of the occurrences of the word Hadoop show up in one task, all of the words like, you know, MapReduce show up in another, and so forth. And then the final reduce step, excuse me, I'm coming off a cold. If I cough up a lung, I apologize in advance. So all the reduce task has to do is get together all of the Hadoop occurrences and then build this longer list of, here's the word Hadoop in the first column, and again, these are just files I'm writing out, tab delimited or whatever. And then I'll have this list of key value pairs that are, you know, each of these document references, URLs, whatever, and the counts. And I'll probably even order by the count so that I have the most frequently occurring document first in this list or whatever. So it's conceptually not a complex algorithm. The whole chain here is, you know, just all in one place. Once you sort of get the gist of what a mapper is supposed to do in a reducer, then this, you know, falls out reasonably quickly. It's not that hard to do. Unfortunately, you know, there are some things that maybe we don't like about this. The first is that non-trivial algorithms are actually really hard to implement in this simple, overly simple model. For example, if you're used to writing SQL queries, if you've ever written a query like, all right, select star from some table, you know, sort ascending by the date, sort descending by the user ID, that is a nasty thing to write in that MapReduce API. You can do it, but it's one of those really, it's like writing Java bytecode or assembly. It's one of those specialized skills that very few people should have to know. It turns out that, as we'll see, there's really a right way to think about these data transformation problems that really wasn't that aware to people, you know, a decade ago. And so the way this code is written in this Java MapReduce code, the way that things are organized conceptually, it's actually hard to actually optimize the performance. So some of the things I just said already, like, well, they end up flushing everything to disk, they really didn't quite know how to make it more efficient in that way in this original model. So we kind of keep hitting these walls of awkwardness and inflexibility and low performance that really are a problem for us. So we don't want to do this kind of stuff if we can come up with a better way. And that better way, I'm going to argue, is Spark. It's not the only way, but it turns out that this is a Berkeley University research project that's been going on now for quite a few years, started as a grad student project, as you might imagine, that really, you know, it's not perfect, but it addresses a lot of these problems in a very elegant way. And that is actually sort of officially being endorsed now by the Hadoop vendors like Cloudera as the next generation compute model for Hadoop clusters. And they're basically starting to retire MapReduce as a result. So what about Spark? What's it all about? Well, it's a cluster compute model, sort of like MapReduce, but it's a lot more flexible. It was actually designed before Hadoop was really very popular, so it runs completely standalone. I often teach it in local mode where we're just running on our laptops. You can run it in Hadoop now in this so-called YARN, which is their acronym for the second generation resource manager, yet another resource negotiator, I think is what that stands for. And there's another Berkeley project, a cluster management system called Mesos that's more efficient than YARN, more flexible and dynamic. And there's a company called Mesosphere, by the way, that's productizing Mesos. There's also ways to run it in Amazon and EC2, either as part of Amazon's, I guess you'd call it distribution of MapReduce, called Elastic MapReduce, or standalone in Amazon. So there's a lot of deployment options you have depending on your needs and how. If you're very conservative, you'll probably want to run it inside Hadoop because you can get commercial support. If you don't care so much about being conservative, if you're willing to go for the more performant approach, then probably Mesos is a better choice. The other important thing about fixing problems about the awkwardness of the compute model, the inability to optimize it because it's so coarse-grained and kind of glommed together, is that it really exposes the right kind of operations that are, you'll often hear the word combinators used for this, that allow us to compose algorithms. And we're going to see examples of this in a minute. One of the core concepts that addresses performance is what they call resilient distributed data sets. So these are essentially distributed collections that live across the cluster. So it looks like you're talking to one collection of user IDs and documents to word mappings and so forth. But it's actually distributed over a cluster. It's resilient in the sense that if one of the clusters crashes and you lose the data that's resident there, it can reconstruct it from original sources, so you don't have to completely restart everything you're doing. That's especially important for the streaming mode of Spark, where you might have some long-running process that's ingesting data and processing it on the fly. It's written in Scala, but there are APIs for Java and Python. There's one actually under production for R as well that'll probably come online before too long. So let's actually look at the code for this algorithm that we just saw. And first, I'm going to torch you a little bit with the Java MapReduce, the Hadoop API version. And actually, I'm not even going to show you the same algorithm. I'm going to show you a slightly dumbed down version where I don't include the counts that I had passing around. I'm just going to pass words and document IDs. And what you would end up with is duplicate entries for a document where it appears a lot, and then you could do counting as a second step. But we're actually going to go with a simpler version. I'm not going to go through all of the details because I don't want everyone to kind of die on me, but I do want to highlight a few things. In all of the code listings for the Scala and Java, I'm going to highlight functions or methods in yellow. And the reason is I want to make the case that all the real work is done in functions. In object-oriented design, we tend to emphasize structure, like, oh, I've got person object, and I've got a shopping list, and this kind of stuff. But really, what pays the bills is the actual functions that are doing work. They're manipulating data, that are returning results, and so forth. But if you look at the functions here, as we kind of scroll through this example, and think about how much work each one is doing, they're actually low-value functions. They're doing trivial things. They're doing stuff that's not terribly relevant to the problem. There's just a whole lot of boilerplate. And a lot of the boilerplate is actually ceremony for the Hadoop ecosystem, not so much my problem, which is I want to index the interwebs. So you define a typical main class. All of this first stuff is just setting it up. And I have to tell it nonsense that it can't figure out for itself, like what's the name of the class that implements the mapper, what's the name of the class for the reducer. You do have to tell it where the paths are of input and output. That's reasonable. I get all choked up when I talk about this. Anyway, there's just a lot of boilerplate. Finally, we get to run our job. We catch all the usual exceptions and print stack traces for what it's worth. The next class is the actual mapper class. This does that tokenization. And you read this thing and your eyes are bleeding by now, and I don't know what's going on. I see the word map because I highlighted it for you. That tells you maybe this is the key method. And sure enough, it is. And down in here, we finally get into the real business, which is I'm going to convert this to lowercase. I'm going to tokenize it by something, string tokenizer. And then I'll just iterate through the tokens using the noisy iterator API. And the output collector stuff, that's how you write out to the socket that's going to get sent down to the reducers. Just a whole lot of boilerplate. Brian had a great example this morning of something he put up and said, all right, 5 seconds, tell me what this does. And of course, there's no way because you were so busy trying to figure out the code. Very much the same kind of problem here. And unfortunately, we're not done. Here's the reduce step, and I won't go through all this, but basically, we're just going to iterate through all the junk that came into the reducer and print out the final thing and bore ourselves to death. Basically, so we've got a software development problem. This is hard enough to program. I'm going to have to unit test the hell out of this, and then acceptance test it. I've got a QA department. It becomes a sprint to do this. It basically sucks because it's not really that hard an algorithm. And there's the whole thing on the left in 6-point. It's actually 6-point font, just so you know, but that's how small it is on the screen. All right, well, let's see what this really should be like in Spark. I should say that the first one was about 90 to 100 lines of code. This is about 45 to 50 lines of code. So I do some imports. I also need a main routine. That object inverted index, it turns out Scala basically makes the singleton design pattern a first-class citizen. So instead of doing static methods and static data, you just declare an object and put stuff in there. But otherwise, just think of that as like normal class, static main, and you're golden. We start by creating a context. That's sort of just what you might do to just tell. This is about all of the infrastructure you have to put in the Spark program to say that I'm actually working with Spark. And then I'm going to start reading a data file. And I want you to notice sort of the structure of the code that follows from here on out. Notice there's a dot in front of most of these words. I'm basically building up a pipeline of data processing. It's a lazy pipeline like the streams pipeline that Brian was talking about this morning, where I'm just going to define how everything should flow, and then finally, at the end, it'll just start running across my cluster, and I'll turn on the spigot, and all this data is going to flow through it. He showed examples of lambdas this morning where it was like arguments, arrow, function body. Well, in Scala, they just use the double arrow like the Ruby hash rocket instead of a single bar arrow. But that's basically it. So when you see map there, I'm mapping over each line, and I'm just using the name line for the variable, and then I'm going to split it on tabs because I said this was tab delimited data. Just by the first 2 tabs, because I might have embedded tabs in the document. And that bit where I return, parentheses, arrow, 0, parentheses, etc., that's actually a tuple. That's the literal syntax for a tuple. So I'm just returning a 2-element tuple where the first thing will be the name of this document or URL or whatever it is. And the second array element will actually be the entire document that I pulled out of this line of text. And then we walk through this sequence of transformations. Now, this is not the most efficient implementation. I could combine some of these steps, but I went for simplicity of concept. In FlatMap, this is the case where I've got a line of text. Notice I'm passing in path and text, path being like the document UID, URL, whatever. The case keyword is about pattern matching. So I'm pulling out of this tuple my identifier, my text. I'm splitting the text on alphanumeric characters. And then I'm going to map over that to return a new tuple that's each word followed by the path. And that's going to be per line. So I've actually returned a collection, collection, collection for each line, and the flat in FlatMap just flattens it all into one big thing. So I'll have this one long list of words and path pairs. That's a bit ugly, but when we get down to the rest, then it starts to look nice. So here's where we use a few tricks that you kind of learn from doing this big data stuff. I want to be able to count. Unlike that Java version I showed you, I am going to keep these counts. So I'm just, in this next map step, I'm going to append a count of 1 to each of these word path pairs. I would have used the words word and path, but I was running out of horizontal space on the slide, so bear with me there. Reduce by key is a built-in in Spark where I'm going to treat each of these words and paths as my key, but I've got a bunch of duplicates. I want to bring those duplicates together and then sum all those ones into a final count per document. And then in the next map step, and I just want to stop for a second and say that even if you don't follow everything about the syntax or everything I'm saying, I hope you can appreciate kind of the elegance and concision of this example. That I've got these yellow words that are expressing operations. I'm combining them together into a pipeline, and then I'm doing very simple steps that look just like closure, actually, on the insides for all of you closure guys. I've got plenty of parentheses, so you should be happy. But I mean, I love this example because it's just very elegant. There's no ceremony about the Hadoop or Spark ecosystem. I'm just manipulating tuples of data, which is really what SQL records are, right? And that's, to me, just fantastic because once I've gotten a few of these little operations under my belt, then I can just knock this out really fast. This reminds me of another beautiful DSL that I fell in love with in college. Anybody know what these are? They're Maxwell's equations that unified electricity and magnetism in the 19th century of the first grand unified theory. Anyway, I love these. I used to have a t-shirt on these when I was a geek. But anyway, but making the point that we've got this beautiful DSL we're building. We're adding up, we're counting all of these word path pairs. The next map step is just shifting things around a bit because I really want the word by itself to be the key. The output I want to be this other tuple of the path and the count. And now I want to group over the words. Actually, this is probably unnecessary because I already did reduce by key, but oh, no, sorry, this is not unnecessary because I need to get all the words together independent of the path and count. And then I do a final output where this is actually what was the reduce step in the other program. I'm basically reformatting this into nice, pretty strings that I'm going to write out. So this is really the end of the step. This is kind of ugly, but that's what I have to do. And then yellow here, you'll see this in the slides when you download them as well. I'm just trying to remind you what each of these things actually looks like that's coming out of each little pipe in this stream. And for example, the group by output looks like this, where I'll have a word, and then I'll have some sequence of those words followed by the paths and the counts. And actually, part of what the map step is doing is stripping out those redundant words, because I don't need them repeated. I've already got it on the left-hand side. So just a little bit of cleanup that's not actually required, but it makes it cleaner. And then finally, back to a little bit of Spark-isms. I have to tell it what I want to do with it, so I'm just going to write it out. I guess argz was actually, I left a little bit out of this, but that's basically the output path that I set on the command line. I want you to write the results here. And then I stop everything. And yeah, just a little bit more detail about what it's doing. So there it is all together. You can actually maybe make out a few more of the letters since it's actually 12-point font in this case. But what I hope you really appreciate, without maybe understanding any of the details, is something that again, you've seen this several times today already. We seem to be converging on this idea of these fundamental operations that we join together where we pipe data in, manipulate it, pipe it out, glue them together to build our pipeline, and we end up with something that's extremely concise, extremely powerful, extremely flexible, and we don't have to worry about this heinous low-level, assembly-level programming that we've had to do for so long. It took me about 30 minutes to write that code the first time. Now, I tweaked it a little bit afterwards, like to clean up the output. I would probably spend another hour just to eliminate some of the inefficient steps, make it more efficient if I really cared. Otherwise, I just throw it on my cluster and run it. I basically took a software engineering problem, which was that ugly stuff we started with, and turned it into a script that I don't need QA on anymore. I can deploy it and run it. If it's not quite right, I'll just fix it and do it again. It actually not only just makes your life more pleasant because the API is a more pleasant experience, it actually changes the game about how you write code when you can have something that is so perfectly tuned to the problem that you're working in. And I think that's sort of a big theme here, but whether it's Spark or one of the competitors you're using, whether you're doing other kinds of reactive programming, which this isn't specifically reactive, but if you think about what you should really desire is either languages and/or toolkits that let you express your problem in the most concise way, and that eliminates so many other problems in terms of getting from concept to running code. And that's why the Hadoop community is really embracing Spark and why I particularly like it too. There are some other pieces that are built on top of this ecosystem in much the same way that there have been tools added on top of the core MapReduce model in Hadoop. I mentioned this SQL query tool called Hive, which was something that Facebook wrote for MapReduce. And in my opinion, it's probably the most important reason that Hadoop is as famous as it is, because if you walk into a typical enterprise, and most of you know exactly what I mean when I say this, you'll have like a few overworked system administrators at the bottom with the duct tape and the baling wire that are keeping things running. You'll have a handful of developers that know how to hack Perl or SQL or Java or whatever to basically do like the ETL gluing of stuff and things like that. And then you'll have rooms and rooms of data analysts that know how to use SAS, that know SQL, but that's, they're not programmers, right, in the usual sense. And when Facebook ran into this problem, and they were one of the first big users of Hadoop, they actually wrote a Hive tool so their data analysts could query this massive data set they were accumulating. And that turned out to be hugely beneficial for everybody that wanted to use Hadoop. The problem is Hive runs on top of MapReduce, so even when you're doing like a toy example to learn Hive, you'll still wait 20 seconds or so for every query, which you would consider nonsensical if you were using Oracle or whatever over considerably larger data sets. But the query API is fairly straightforward. It's basically just a dialect of SQL, so the Spark guys ported it to Spark and called it Shark, for better or worse. And then you get to do really cool stuff that in SQL when that's the easiest thing to do. So I was sort of a typical Java developer for a long time where I basically hated databases. I hated DBAs. I'm not sure what it was, but I wanted to get that data out of that database as fast as I could and get it into my perfect model of the world object model and then never think about the database again. But it was when I started working in big data that I really came to love SQL, which is kind of ironic to say because big data it's no SQL, man. We don't do that stuff anymore. But no, actually we really need this. Just side note, SQL is roaring back. If you haven't noticed, all of your NoSQL databases are trying to add a SQL abstraction, Cassandra being Exhibit A. Anyway, but it's really nice if I have this data that's semi-structured or structured, maybe comma delimited, tab delimited in my file system, and I can layer this abstraction on top, like in this example of stock data. And then I can write queries like this one that gives me the year-over-year average closing price of Apple stock, which is amusing to look at because then you realize when you should have bought Apple or when you should have sold it, as the case may be, in the last few years. But even Spark cannot compare to the concision of something like a SQL query. So my model in big data has been, if I can write it in a SQL query, I'll do it. I'll use Hive or Shark or Impala as this other thing. If I need something that doesn't quite fit the query model, then I'll use Spark or something like that. And just because of this caching, I guess I didn't quite say this, but when I was talking about these resilient distributed data sets, the other key feature they add is that they will cache data in memory so that when you have a sequence of operations coming through, you're not going to read the data from disk every time. And just because of that feature, they get 10 to 100 times the performance of Hive for identical queries over the same data sets in HDFS. But the other contributing factor, and actually it's interesting to read blog posts by the Spark team when they talk about how hard it is to fix bugs in the Hive code base, which is sort of ugly MapReduce Java, versus, and maybe they're being a little biased, but versus their own code, they find it vastly faster to fix things because they just have better abstractions internally for manipulating data. There's another interesting thing they're developing now called Spark SQL, which is essentially a new query tool that sits underneath the hood of whatever API you're using. It will eventually replace the guts of Shark. But what it lets you do right now is it lets you embed SQL queries in your Spark jobs so that you can glue it together with other API code like machine learning libraries. So this example I stole right off the blog post that's linked to in the speaker notes. But basically imagine that I have some user data and some event data, and this is a situation where maybe the event data is like there's parties happening at this location in your city, and notice this subscribe flag at the end of the schema for users. What I want to do is build a predictive engine that says if you're not already subscribed to events happening in your neighborhood, then I'm going to recommend that you subscribe to them. That's sort of the basic thing I want to do with this example. I have these Hive tables that I defined in the traditional way with Hive tools or Spark queries, whatever, Shark queries, sorry. And then here I'm back to Spark where I now have this new method called SQL. This is a bit ugly, but I have to use strings, unfortunately, but nevertheless, I can use multi-line strings with this triple quote convention in Scala, so it at least looks normal. And I can just write a query where I'm going to select I'm actually doing a join here, and I want to join up users and events based on the user ID. And I'm going to use that as training data, so I'm training some machine learning algorithm. You can see at the bottom it's going to be logistic regression with stochastic gradient descent. If those words mean anything to you, great. It doesn't really matter for our purposes. But just imagine I'm trying to create a recommendation engine, gluing SQL queries together with this MapReduce, this machine learning library. And then later I can do a query that says, all right, give me all of the potential candidates for this notification service, people who are not already subscribed. Notice the where clause. I'll define some classes for like scoring an individual to see who's the most likely to be interested in this feature. The notion of features that you see there in the middle, that's sort of a classic machine learning term for the kind of criteria I'm using, like the location, their age, maybe their gender, that kind of stuff. And then from these people, I'm going to predict how likely it is they're interested in this stuff. And I'm going to save, this is a really cool feature. Register as table means, that SQL query I did initially is actually creating these RDDs in memory. I'm creating a new set of RDDs called score that has a 2-element schema, user ID and score at the top. And now with this one method call, I can just write that as a Hive table back to Hadoop, which is very convenient. And then I can do my final query where I want to get the top 100 people that have a high by score. And I should say that if you know SQL really well and you are really paying attention to these SQL queries I've been showing you, the Hive SQL is a bit off in some respects. They do depart from, well, there's no standard SQL, right? But they're a little more aggressive about breaking ANSI conventions. But nevertheless, you can learn the SQL pretty quickly and embed these queries with this API right in the middle of your Spark code, and then all of a sudden you get results that you can then use to predict, these 100 users are the ones I should be contacting for doing things. Okay, a few more pieces of the ecosystem I'll talk about. One of the reasons that, let's put it this way, one of the other real pain points with MapReduce is that it really is very much oriented towards batch mode computing. Because there's so much overhead in setting up this set of tasks, it's really not suitable for the case where, it's not fast enough for me to just run, an update to my inverted index every 2 hours. I'd really like to update it incrementally as the web is changing because it's constantly evolving. Or in the case I just showed you, I'd really like to be making predictions and updating the training of my machine learning algorithms as events are happening, not like once a day or something, because that's time that things are actually out of date. So it's becoming increasingly important for us to be able to do quote-unquote real-time event stream processing. I used to do embedded systems years ago, so their notion of real-time is a little bit different than this notion. But the idea is that as events come in, I'd really like to be able to operate on them in some relatively fast period of time. And the way that Spark implemented this, which was originally implemented like MapReduce in the sense that it was oriented towards batch mode computing, is that they said, all right, what we'll do is we'll let you define windows of time. We'll capture everything that happens in those windows of time, like say 1 second windows. And then we'll run an iteration of whatever data flow you've defined as part of your job on that bit of data. And they're not going to start new JVM processes each time. It's not that inefficient. But they use this granularity as a way of fitting their existing model into this streaming model. So if you really do need something that does react on every single event, sort of like maybe more like a traditional message queue or something, this may not be the tool for you. But for a very large number of applications, it's good enough to just grab like second or minute intervals of data and then incrementally update, counts, averages, machine learning algorithms or models and so forth. And so I did this diagram about an hour ago, and it's a bit of a hack, but nevertheless, so I'll grab the first iteration, increment of data and run an iteration of my algorithm. The next one I'll run another iteration and so forth to process it. So this is the closest I'm going to get to talking about reactive programming. I know we're all supposed to mention it in all the talks in this conference, but so I did at least fulfill my obligation to mention reactive programming. And the code, though, here's the nice thing. The code looks very similar. You get this uniform representation, whether it's batch mode or streaming. There are a few differences. You use a streaming context now that you wrap a traditional Spark context. You typically will be interfacing to a different source of data. Like in this case, I'm going to connect to some server and port with a socket. But then everything below that just kind of falls out the way it did before. Where in this case, I stole another example off the Spark website, and this is the traditional word count algorithm where I just want to find all the words in this stream of data and count the occurrences of all the words. So every time a line of text comes in, I'm going to split it on white space, and that'll output a collection of words. And then I'm going to, in the next map step, I'll add a count of 1 to the end of each word, create a tuple there of word and count of 1. There's that reduced by key again that we saw earlier. So the reduced by key means it's going to find all the same words, bring them together, and then apply this function to them. It'll take the count of 1, the count out of the other, which is the value part of this key value pair, and then sum them up. So the output of that will be a list of all the unique words and then a count of those words in this stream. And then I might print out some of them. You would probably do something more intelligent than that. But nevertheless, what's interesting is the last two function calls are also new. Now we have to explicitly start the stream running and then await for termination. Termination could be because the socket closed, or if we're reading some static source of like file data, then it might just terminate because we hit the end of file, that sort of thing. Or we Control-C out of it, which is the official way you're supposed to shut down services gracefully. Just in passing, I'll mention one last thing, which is the machine learning library. Actually, Ellen, just in that room in the previous hour, talked about Hoot, which has officially decided to port all of their machine learning libraries and math library to Spark, which is going to be pretty exciting. There is a basic one already. It's not terribly complete, but it does have some support for a few of the classic machine learning algorithms, like linear regression, where I want to fit data to a line and then predict new things based on that line. Binary classification would be like spam filtering. Is it spam or is it not spam? True, false, 1, 0 kind of classification. Collaborative filtering is kind of an old name for recommendation engines, where if you appear to be very similar to this guy and he's watched movie XYZ and you've watched movie UVX or something, then maybe you want to see Z, that kind of stuff. Clustering is a kind of machine learning algorithm where you don't train the system in advance like the others. You actually just look for structure in data that you don't know whether there's any structure or not. And then there's some other algorithms as well, but just to summarize that quickly. And actually, I guess it was one other piece that they've added, which is sort of more bleeding edge. If you think about like social networks, are actually giant graphs of relationships, and distributed graphs are actually sort of at the bleeding edge of computer science research in a lot of ways. There are some implementations of distributed graph systems, but it's still common for people to use sort of other hacky representations, like use giant matrices to represent relationships and process them in more traditional ways. But there is a lot of work happening in graph theory, in graph algorithms, and Spark is trying to grab onto that gravy train too, I guess. So they have a system called GraphX that supports a bunch of these things as well. So if Neo4j isn't good enough for you because you need more than one server, you might check out GraphX, as well as some others. Okay, so to wrap up, this is something I tweeted the other day. It sort of summarizes how I got into functional programming without mentioning the word monad. Oh, damn. 5 or 6 years ago, everyone was talking about functional programming is the correct way to solve the Moore's law of death, that we no longer could scale vertically, that we had to be able to scale horizontally. And it does give us a lot of good ways to think about it. But what I'm actually seeing happening is that a lot more people are, as far as like light bulbs going off, when they see code like that Spark code, which is not any credit to me, it's just the way it is, when they see what Java 8 looks like versus Java 7, you sort of get the gist that maybe if we wanted to distill our code down to the bare essence of the simplest thing that could possibly work with the most concise way of expressing hard problems, that functional programming is actually just tailor-made for data science. So that's, I think, what's going to really drive interest in functional programming. Not the monad stuff, but actually the concepts that it gives us, like combinators for gluing computation together to build more complex algorithms. I actually think those combinators are the best reusable modularity construct we've ever come up with in programming, in ways that objects actually didn't satisfy. So I think that for that reason, I'm sort of riffing at the moment, but if you think about why object-oriented programming got popular, and some of us were around when that happened, it was largely because user interfaces seemed like such a great fit for objects. It was just a natural way to think about this little widget, nice and contained state and behavior. And it really was the right way to think about it. But then once we got onto that kick, we started applying it to everything. Well, I think that's going to happen here. A lot of us, and I've talked to companies where they were like pure Java shops and weren't going to consider anything else, and suddenly they bought a Hadoop cluster and found out it was a lot easier to use Spark or Scalding than the Java API, Scalding being a Twitter API that's very much like Spark. And that's sort of what tipped or flipped the switch maybe to think about functional versus object-oriented programming. I think we'll see the same thing. A lot of people will start doing this kind of stuff in a functional way, and then they'll realize, we can do UIs this way, we can do anything this way, and we'll start drinking that Kool-Aid. Start using that approach for a while. So, final thought, just to conclude. So it's really a very flexible, very well-designed, deeply rooted in computer science best practice, well, that's a lousy word, theory, computer science theory and thinking about distributed systems that is finally coming into its own, finally being embraced by industry as sort of the next top compute model. And I really encourage you to check it out, especially if you're doing anything with Hadoop. If you have Cloudera's distribution of Hadoop, you've already got Spark if you've upgraded to CDH5. So it's really worth checking out. And I think Hortonworks is, MapR has announced that they're going to support it too. Okay, any questions? Yeah.
One comment I found that the if you're on a Mac, the do to Docker, somebody has a Spark Docker. It took me 5 minutes to just run that, do a couple Spark things.
Really?
And that usually takes a lot longer to get something new. So that was a fairly impressive.
Huh, interesting. Yeah. Yeah, I've actually, TypeSafe does these activator templates, sort of examples of different APIs, and I'm working on one for Spark. And it's compared to Hadoop, it's wonderful that you can just run it on your Mac, and you can debug your algorithm, make sure it's right, use some real data, and then deploy it to a cluster, and of course it'll crash or in some way. But at least you know that it's not the logic of the code, right? So, any other questions? All right, thank you very much.